Hey guys, welcome. I got some good news and some bad news. The bad news is that this is already the last day of KubeCon. This is already the last day of KubeCon. But I got some good news also, because we got at least one talk left that's about advanced scheduling. Yay! So this is what we're going to talk about today. We're going to give a small introduction about the company Nerdalize. We're going to create a basic scheduler and then move on to the more advanced stuff. And we're going to wrap up at the end to see what we've done. My name is Ad van der Veer. I'm a product engineer at Nerdalize. This is a Dutch company that's building a cloud. And we're doing it a bit differently. And that's what I'm going to talk about with you about first. This is what a data center used to be. I'm not sure if you were there, but this is a building where people were just manually computing difficult computations. And there is this one person in the middle that's scheduling these jobs. So new computation came in, and we need to find a worker, a controller, that can then take over the job and calculate this single calculation. Luckily, we've came a long way. So this is how a modern data center looks like. As you can see, there are these huge buildings with huge amount of infrastructure, big computers, and a lot of technology. But this is not, everything about the data center is good. So these buildings are incredibly costly, both to build, but also to maintain. You can imagine that all the power redundancy, all the networking, everything needs to be maintained in order to get the servers online. Besides that, there is a lot of energy that needs to be used, and a lot of CO2 that's wasted onto the environment. So that's where we decided to do things a bit differently. What Nerdalize does is we take these computers that you would normally place into the data center and place them in people's homes. And you're saying, well, that's insane. How can you possibly do that? But it turns out that it has three important upsides, both for the owner of the home, the user of the cloud, that's you guys, and the environment. I can tell you about that, but we have a small movie that does a lot better job of it. Streaming from the cloud. Yeah, I can get the offline version.
Something about a startup company, maybe located in Delft, and they wanted to heat houses with the excess heat of computers. And from that first moment, I thought it was a brilliant idea. I thought it was a complete game changer.
Nerdalize is a cloud provider that offers you computing power that is much more affordable and drastically lowers your IT carbon footprint. Instead of stacking a lot of servers together in an expensive data center, we distribute cloud servers over individual households in the Netherlands connected by fiber. With 10 gigabits to each house, our cloud is great for all your high-throughput computations like video transcoding, life science and engineering simulations. By running computations on the Nerdalize cloud, you drastically lower CO2 emissions as the energy is used twice, once for your calculation and once for heating houses. All savings taken into account, your compute can save up to 3 tons of CO2 per household per year. Nerdalize offers you a sustainable cloud solution with irresistible price and performance. You don't pay us for building and maintaining a conventional data center, simply because we don't have one. Compared to other cloud providers, this saves you up to 50% on your cloud bill.
Nerdalize has made it incredibly easy for us to give those options to the biologists. I think it's going to be a no-brainer that biologists are going to be choosing the Nerdalize option because they will have access to the cheapest compute that way. But also, I think there's a real draw from these customers in that they know that they're going to be getting their compute kind of with the lowest carbon footprint possible.
So ask yourself, do you want to lower your IT carbon footprint? Do you also want to cut your cloud expenses by up to 50%? Experience how much you can benefit from the affordable and sustainable Nerdalize cloud. Visit nerdalize.com.
So to recap, going data centerless, moving the machines from the data center to a home, has 3 important propositions. So the homeowner can save up to 200 euros per year on his heating bill. The environment saves up to 2 tons of CO2 per year. And you, the cloud user, can save up to 40% on his cloud bill. And in order to prove that, we set up a Kubernetes cluster on our own cloud. We got one of our customers involved, and we ran an actual workload. And it turns out that indeed, if you compare this to other instances on an actual workload, you can save up to 40 to 50% of your cloud cost. And now you say, okay, that's all fine and good. Tell me about this technology. How is this even possible? And we got many, many challenges that we managed to solve in the past year. And today I'm just going to talk about one of them. How can we schedule these jobs? So Kubernetes is pretty good at taking a job, looking at the CPU, see where some resources are available, and then moving the job to the correct node, just on CPU and RAM. But we got another problem, right? So this is Jos, this is one of our homeowners, and currently he's not using any heat. He's enjoying his 200 euros of savings, doesn't need any heat at all. But at the other end of the Netherlands, we have Chantal. Chantal is in need of some heat, because you can see she's burning her hands on some super hot water. But luckily we got a cloud box there. So this is our product, we installed this in your home. And we got about 160 CPUs in there and a very decent network of about 10 gigabits per second with sub-millisecond latency. And the question is as follows. How can we make sure that Kubernetes schedules these jobs at Chantal and not at Jos? How can we instruct Kubernetes to do this? And luckily, Kubernetes has a scheduler, so I'm not going to ask you to read this like a bunch of text, but I'm going to break it down for you. So there are 3 basic steps. 1, the scheduler gets from the API server, from the Kubernetes API server, pods that are currently unscheduled. And then it's going to find a node, by asking the API server, it's going to find a node that has the right amount of resources available, and then it's going to create a binding. So it's going to create a binding that binds the pod to the node. And the cool thing is that you can write this basic scheduling logic in about 10 lines of bash. For this example, we're going to take a fixed node. So we're going to say every pod is going to be scheduled on this single node. We're going to start an infinite for loop, who's constantly going to ask the API server for pods that are currently unscheduled. So scheduled is set to null, and the schedule name is set to our custom scheduler. And then the only thing we do is we send back a binding. So we use curl, send it back a binding, create a resource, and then say to Kubernetes, schedule this pod on this node. And of course, we're going to create an echo. We're going to print it out, so we're going to make sure that we did our jobs as a developer. And this is all you need. This is creating your own scheduler, a very basic one. But at Nerdalize, we needed something a bit more advanced. So for that, I'm going to invite Boris. He's worked on his bachelor thesis to create a scheduler using Kubernetes that's a bit more advanced. Boris, take the stage.
Thanks, Odd. My name is Boris, and together with Robert, who is going to present in a bit, during our bachelor thesis, we worked on extending Kubernetes, thanks, to include our own custom scheduling logic for the scenario that, that's me, for the scenario that Odd just described. So I'll talk you through how we did that, and then Robert is going to give a live demonstration of that, and let's pray that the internet connection is then working. So to show you how we did that, I'll first need to talk you through some background. So what you're looking at is a simulated little toy example with 3 homes in our Nerdalize network. And then, as Odd said, each of these homes has a bunch of Nerdalize servers in them. But it also has a boiler or a water reservoir. And this can be used as a buffer to store the heat that's generated by the computers. We constantly measure the temperature of this water with one of our devices. And then we report it back to Kubernetes as a node annotation. So now we have some information about the temperatures in the system, and we can make some cool scheduling decisions about that. So when a home uses some warm water, the value of the boiler temperature decreases. So for example, if Jos here would take a shower, his temperature would drop. The same thing goes the other way around. When a pod is scheduled on a node, it will start making CPU cycles and warm up the computer, warm up the boiler, and then the home gets warmed. So for example, Chantal here, if we schedule a pod there, then obviously the boiler starts to warm up. And as I said, this thing is constantly measured, such that we're constantly aware of the current state of the cluster. So let me explain the scheduling policy that we introduced, which is a very simple yet very effective scheduling policy if you want to reduce the heat that is wasted. Because if the boiler reaches its maximum temperature, which is 55 degrees Celsius in our case, we cannot store the heat in the boiler anymore, so it will be vented outside. But if there's other boilers in the system that are still in need of some energy, we can obviously schedule there and let it make use of the heat. So this is our scheduling policy. What you're looking at is 3 bar graphs, each representing the boiler temperature of the home. And then if a new pod would be scheduled, we expect it to go to Alex's home, right? Because it has the lowest boiler temperature. So this is indeed what happens. And then when a new pod comes in, now Chantal has the lowest boiler temperature, so expect it to go there. And this goes on and on and on. So now that the boiler temperatures are saturated, we can still schedule our pods because our computers are still available. But as I said, now the heat will be vented outside, so we consider this a waste. So how do you do this in Kubernetes? How can you add your own scheduling logic? That's what I'll talk about now. And then first I want to talk to you about how the normal scheduling is done in Kubernetes. So what you're looking at is kubectl on the left, and you're all familiar with this, hopefully. It's the client interface that allows you to talk to the Kubernetes cluster. Then you have the API server, which is the server interface, which all components communicate through. And then the scheduler is one of these components. And the scheduler is now presented with the task of scheduling a pod, with this, in this case, requested 7 CPUs and 1 gigabyte of RAM. So it looks at the nodes that it has at its disposal and finds out that there's 2 nodes in the cluster, the first and the second, that can actually take or handle this pod. So because they only have like 2 and 1 CPU running at the moment. It will then do some more things, like it will sort the nodes even to see like which is the most optimal. So it'll probably schedule on the second because it has the most space available. So that's all really cool and well, but how do we instruct it to take our heat into account? Because this is our scenario, right? We have all the CPU and RAM conditions still there, but we now also want to take the heat into account. Well, the really cool thing is that Kubernetes allows you to deploy an extra scheduler. We call that heat scheduler in this case, and that's like the same block. So it's basically the same thing. It's just the vanilla kube scheduler. It still does its logic like before, so it still takes into account hardware, resource constraints, and all that. But we can now extend it with an extender, and this is where we can define our logic. So it will talk over HTTP and present the extender with a pod and a node list. And then it can do its own magic, so sort the nodes however it likes, and then return the node list and say, hey, this is my preference of scheduling. Take this into account. So I will show you in a bit more depth in code how that could look like, because it can be done in just a few lines of code, actually. This is the configuration file of the heat scheduler. So there's 2 containers running inside this pod, and the first one, as you see, is just the raw kube scheduler binary. So it still does the same thing, but now we can define a policy config map, which is shown on the right. And here you have the power to give like the normal predicates that are also in the normal kube scheduler. So pod fits resources, for example, takes into account CPU and RAM in the nodes. But we can now also supply our extender. So it's the HTTP endpoint that it will talk to, which is going to be in the same pod on port 8100, which is the second container here. And this is where we handle the incoming request and do our own scheduling logic. And yeah, so let me show you how that extended then works. That can be described in just 3 basic steps, actually. What I'm showing here is a bit of Go code. It's a bit stripped down to like get rid of all the verbose, error handling and all that, but this is actually the thing that you could run. So at first it will handle the incoming HTTP request and decode the JSON object and all that. But then in the second step, this is where we can do our thing. So we'll loop and try to find the node that has the lowest annotation Nerdalize temp for temperature. So now we have the minimum value of boiler temperature in the system. And then in the second loop, we can find the corresponding node and then respond the Whoops. That went way. Oops. Yeah. Then respond with the node that has the lowest boiler temperature. So it's giving it back to the kube scheduler or heat scheduler in this case, and then it will sort it or schedule it on this node. And to see what the impact could be of such a little scheduling decision, we conducted an experiment in which we envisioned the following scenario. We simulated 50 homes, each with his own boiler, and then we assumed 4 people on average per household, so that's 2 parents and 2 kids. And we wanted to compare the default scheduler with the or with our heat scheduler in terms of heat waste. So the scenario is as follows: kids take a shower for 15 minutes, then the boiler warms up for 1.5 hours, and then before they go to bed, the parents also take a shower of 15 minutes. And the results look like that, and that's a lot, so I'll talk you through it. There's 2 graphs, each of them containing 50 lines, so that's 50 boiler temperatures for each of the households. And you see the scenario on top, so kids taking a shower, so boiler temperatures drop, boiler warming up, you see the lines going up, and parents taking a shower. And then there's 2 red bars that you should know, one on the top and one on the bottom. And the one on the top is where that's like temperatures that the boiler can actually not reach. So this is where we would vent out heat instead of store it in the boiler. But if there's other boilers in the system that can still use the heat, obviously that's a big waste. And then in the bottom bar you see temperatures that that are colder than the coldest boiler temperature. So now we need an external source to heat up the water, and that's also a waste if you could distribute the heat more evenly in the system. So what you see is that with a heat scheduler it stays good within the bounds, but with the default scheduler it just doesn't take the heat into account, so it jumps through the red bars. And the result of that is that we can reduce CO2 emissions with an additional 10% when also like additional to what we can already do with Nerdalize with just a few lines of scheduling code. So that's really cool. Robert is now going to give you a live demonstration of how that all works. So let's pray that the internet connection still works.
Hello? Yay! All right. So my name is Robert. To show you that this all actually works, I've prepared a little demo for you. Let's hope it works. So for this demo, we have a 3-node Kubernetes cluster, as can be seen here. Yay. All right, so there are 3 nodes, and each of these nodes correspond to a household. Now this means that there's a server with a boiler attached, and the boiler is getting heated up by the compute that is generated on the server. The boilers have a temperature which is added to the Kubernetes node as annotations. So we should be able to see this if we describe the nodes and we grep for the annotation. So as we can see, there are 3 homes: Chantal with a boiler temperature of 43, Jos 37, and Alex 24. So for convenience, we can graph these values as bar charts to make it similar to what you saw in the slides. So higher bars mean higher boiler temperatures. So let's see if we can schedule some compute on this cluster. So to do that, we have defined a job, which is essentially a finite pod in Kubernetes. And this job uses the Nerdalize heavy data cruncher image, which, as you can imagine, does some serious data crunching. So let's see if we submit this to the API server. We should watch the pods here. We can see it gets assigned to Chantal's household. The boiler heats up nicely. This is sped up for simulation purposes. It wouldn't go this fast in reality. And we can see that at some point the boiler reaches maximum temperature, and all heat generated after that is essentially wasted. So we want to prevent that. At the same time, we can see that Alex's household, his boiler is much colder, so he could make much better use of that heat. So ideally, we would schedule it there. And to do that, we need to introduce the notion of boiler temperatures and instruct Kubernetes scheduler how to deal with this. So let's see how we can do that. So we edit the spec, and we add the scheduler name, and we set it equal to heat scheduler. So what this does is it tells Kubernetes scheduler to leave this alone, not to schedule this pod, and essentially it tells the scheduler, we have our own scheduler, it's called heat scheduler, which will take care of scheduling this pod according to our own logic. So if we submit this, we should see it showing up at the bottom right, and it does in fact, but it remains pending. And this is expected because our scheduler is not yet running. So to actually run our scheduler, we need to do two things. This is the same deployment you saw in the slides. I'm going to run you through it again, just to freshen up your memory. So it has two containers. They run in the same pod. One is the heat scheduler, which is a copy of the default Kubernetes scheduler. So we just get it from the mirror Google containers repository. We pass in the scheduler name, which is heat scheduler, and we pass in the config map, which is scheduler config. And this config map actually describes how this scheduler should operate. So, oh, that's very loud. So this is the config. Does it work? It works. Okay. All right. So the config map describes how we configure our scheduler. So we can use the predicates that are defined in the default Kubernetes scheduler, which is desirable, because that means we don't have to implement them in our own scheduler. So we use the three most common ones to make sure that the node is suitable. And when the scheduler narrowed down the list of all nodes to the list of suitable nodes, it hands it off to our extender. And the extender runs in the same pod. They communicate over localhost, and our extender is responsible for choosing the node with the lowest boiler temperature. So this can be seen here. The extender is running. That is the Go code that Boris showed in the slides. So if we create this, the config, and we create the heat scheduler itself, we expect the status here to change from pending to running, and it should be scheduled on Alex's household, because that is currently the coldest one. So that is indeed the case. Alex's household is heating up nicely, and at some point we see that its temperature reaches a higher level than Jos's household. So that means that if we create another job, we expect it to be scheduled on Jos's household. So we submit it, and as expected, it gets scheduled on Jos's household. His boiler is heating up. So let's do that one more time, just for the hell of it. So that one gets scheduled on Alex's household, which was the coldest at the time. And as a result, we can see that the heat is nicely distributed across all the households. We minimize the waste of heat. And Chantal, Jos, and Alex can take a nice, hot, free shower. That was a demo. I'm glad it worked. Thank you.
So let me recap that for a minute. we got a pretty awesome idea at Nerdalize, but then we add 5 lines of code to a scheduler, and we make the ID 10% better. I think that's pretty amazing. So what's the Baxter question? What more can we do with such a scheduler? And we came up with 2 extra ideas. So what if we don't look at the minimum boiler temperature, but instead look at the forecasted amount, or, oh wait, let's recap the boiler temperature first. So this is what we did, right? So we looked at the minimum boiler temperature, scheduled the pods. But what if we look a bit further? So what if we look instead at the forecasted temperature of the pod? You can imagine that if it arrives at a boiler, or at a server that heats a boiler, it doesn't heat up the boiler immediately. So we have to kind of forecast how much heat it's going to produce, instead of assuming that it heats up immediately. So instead we add a policy that looks at the forecasted amount of heat that's going to be generated. So in this case, we got one there, it's forecasted, and then Chantal's forecasted heat is the second highest, and so on, and so on. The next one I think is even more interesting. So what if we could forecast how much heat a certain home needs? What if we could look at the climate, for example? Maybe Chantal lives at a place that is a lot colder, so she needs more heat in the winter, for example. So what if we take into account the difference between the forecasted heat and the actual boiler temperature? So we schedule pods on places where we expect the difference to be the highest. That would look like this. So we take a job, we take a pod, and we place it at Chantal first. Then the second biggest difference, probably Chantal. And then we place the third one at Alex, and the next one at Jos. At this point, you can switch back over to the old scheduling policy. So the next pod that comes along is placed at Alex, and so forth. So what can this do for you, right? You're probably not heating up the Netherlands with servers, but maybe you got another business. And the cool thing is that the actual business logic is very well isolated in this extender. So it's only the second part of this minimal amount of Go code that you can customize in order to get your own scheduling in there. So maybe you got a bunch of SSDs that you want to use inside your cluster, or maybe you got an advanced machine learning algorithm that you want to use in order to schedule more efficiently across your data center. And this allows you to do that in a very well-defined place. So to wrap up, at Nerdalize, we're creating a data centerless cloud. It allows the homeowner to save on his heating bill. It allows CO2 emissions to be reduced by about 2 tons. And you can get a cloud that's about 40% cheaper than the rest of the world. And what we discovered is that Kubernetes is an excellent fit. Not only because of the standardization that's currently occurring, but in our case, it could save us a considerable amount of CO2. By just implementing a basic batch scheduler, we saw how easy it was to customize its behavior. Then we went ahead and created an extender to get our business case in there. And then we ran an experiment to show that it actually worked. And it proved that we could save up to 10% extra CO2 emissions per household per year, which is a great amount. If you're interested to look at the code, visit our GitHub. If you got inspired and you want to work at Nerdalize, contact us. You can help too. If you want to heat up the Netherlands with your compute jobs, we just launched our Kubernetes product today. So visit us at this link, get your pods in there, help Jos get through the winter, please. Flyers with more information are at the entrances. And join our mission. Check out our code. And if you have any questions, the Nerdalize crew is up here. And thank you for listening. Are there any questions right now? Yes?
The graph that showed the normal standard scheduling versus the one that you implemented with the simple extension policy, was that an actual measurement or just simulated?
So the question was if the graph that we showed with our custom scheduler, if that was a simulation or it was an actual run. It was a simulation. Any other questions? Oh, sorry. Oh, excellent question. Want to answer this one?
Sure. No, because he saw the hoodie, right, in the video. Yeah, right. Cool. Yeah, so as I said, we warm up boilers, right? And not just heat homes. So in summer, you still need to take your shower and still need warm water for cooking. So that's basically how that's solved.
And once we cover the whole world with our machines, we can just schedule at the other side of the world, right? Yes?
What about rescheduling? Like, do you do any type of rescheduling based on the temperature? Let's say job is running too long and you want to do it.
Yeah, good question. So the question was whether we also reschedule. Maybe a job takes too long or we need to place it somewhere else. We did an experiment with that. Of course, in our case, the redundancy of a single home is quite low. So often the machine might shut down and then we reschedule the job somewhere else. We didn't calculate how much effect it had on the actual CO2 savings. So yes, we did it, but we don't know what the results or what the effects of it is. Any other questions? Cool. Feel free to tap us on the shoulder and thank you very much for being here. Have a nice day.